everybody, and welcome to today's session on improvements to protein gel electrophoresis, both from a chemistry and technology perspective. Now, many of you who are doing basic protein research think that gel electrophoresis is a pretty basic technique that has not changed much over the years. And though that is true, most continue to perform these gels in relatively the same manner they originally learned it in college or in grad school, or perhaps from the labs in which they worked as postdocs. Making small tweaks here and there to these gels, making small improvements along the way so that they can look at their downstream Western blotting or gel staining a little bit better and more improved. However, there have been advancements over the years in protein gels that have differed from the moments a decade or so ago that have made protein gel electrophoresis much more robust and also made a difference in resolution and detection of your protein separation. And those are the small improvements and large technological gaps that we're wanting to touch upon today in this session. Now, in today's session, we're going to go through several things. Broadly speaking, we'll talk about the types of protein gel electrophoresis. We'll highlight specifically SDS-PAGE as the electrophoresis system of choice. We'll go through the different buffer systems that exist in the world of electrophoresis, as well as the gel chemistries that are out there. We'll also talk about these chemical and technological improvements to gel electrophoresis, touching upon both self-casting gel systems, as well as pre-casted gel systems, as well as tank apparatuses and improvements upon those as well. And finally, concluding with the types of choices and decisions and conclusions that you can come from understanding these improvements in gel electrophoresis. Now, the types of gel electrophoresis are varied, although there is one that is predominantly most popular than others. As a quick overview, the basic polyacrylamide gel electrophoresis, or PAGE gel, separates proteins by their native physical properties. This is sometimes often also known as native PAGE gel electrophoresis. The most common form, however, is SDS-PAGE, or sodium diacetyl sulfate PAGE electrophoresis. And this form of electrophoresis solubilizes proteins by coating them with a uniform negative charge, thus disrupting the majority of the non-covalent bonds and reducing their hydrophobicity. SDS-PAGE treatment largely removes differences between proteins in both charge and conformation, making size the main determinant of the electrophoretic mobility. This mobility is used to determine the approximate molecular weights of the proteins with reference to the mobility of the protein standards that are in the same exact gel. In addition to SDS-PAGE and typical native PAGE, there's also reducing and denatured SDS-PAGE, where the addition of DTT or other additives reduce disulfide bridges to achieve better denaturing. As a whole, these are the three major types of protein gel electrophoresis. Now, as an overview, what happens during SDS-PAGE? Well, you first begin with the protein itself. You're then going to add the SDS to that protein. The SDS then binds to the amino acid residues and gives a uniform negative charge, as we mentioned. And with heat, the protein then begins to linearize or denature. Once it's loaded onto the gel, the protein sample is loaded along with a lane marker, typically a set of protein standards that denote the different molecular weights of your protein samples. And then electric current is applied where the negative charge allows the protein to migrate towards the cathode end and separates the gel based upon the electrophoresis properties. Now, beyond choosing the type of gel electrophoresis system that you want to use, choosing the right gel percentage also helps in making sure that you have good and solid protein gel separations. Choosing the right gel percentage is really a function of the protein size that you're looking at. If you have a relatively simple single protein application, straight percentages are great for that. They provide distinct separations of protein sizes. If you're looking for proteins, for example, between the 4 to 40 kilodalton range, a 20% gel will do the trick. If you're looking for proteins around the 10 to 70 range, a 12.5% gel will also do the trick. However, if your application calls for a separation of a mixture of proteins, then a gradient gel percentage is best used. And depending on whether you need to see very low molecular weights as part of your separation or larger molecular weights as part of your separation, you'll choose a different gel percentage gradient that meets your needs. At this time, we'd like to ask you a quick polling question in regards to the type of gel chemistry you commonly use in your applications. Do you use tris glycine gels, bis-tris gels, or tris acid gels? Please take the time right now to answer this quick polling question. Okay. So as related to that polling question, there are various different gel chemistries when it comes to SDS page, the most common form of protein gel electrophoresis. These chemistries include the most widely used tris glycine gel chemistries for small and medium protein separations, and tris glycine uses traditional Laemmli buffers in its protein gel electrophoresis. In addition to tris glycine, there's also bis-tris gel chemistries, which also perform separations along the small to medium protein range. However, there are other specialty chemistries that also exist. Tris acetate chemistries, which are mentioned in the polls, help with better separation along larger molecular weight proteins, and trisine gels allow for better separation along smaller molecular weight proteins. In addition to the type of chemistry, there are also different types of buffer systems, both continuous and discontinuous buffer systems. In a continuous buffer system, it utilizes a same buffer in the gel and the running buffer. Although this is not as popular as the discontinuous system, it is still useful. The most commercially available gels, however, use discontinuous buffer systems. And in a discontinuous buffer system, the two different gel layers offer different pore sizes that result in higher resolution of separation. As an example of the types of discontinuous buffer systems, let's take a look at each one of them as it relates to the three chemistries we had mentioned earlier: tris glycine, bis-tris, and tris acetate. In tris glycine chemistries, the mixture includes glycine, protein SDS complex, and chloride, with a gel operating pH of 9.5. And that's important to note as we talk about improvements to gel electrophoresis. In the bis-tris gel system, it's a mixture of MES or MOPS buffers, protein SDS complexes, and chloride as well. However, the running operating pH is 7.0, a neutral pH. In tris acetate, it's a mixture of trisine, the protein SDS complex, and acetate, with a gel operating pH of 8.1. At this time, we'd like to take another opportunity to ask a polling question to the audience about your experience with your gel electrophoresis when it comes to resolution. Question is, do you ever experience smiling gels or poor band separation during your electrophoresis? Yes or no? Okay, thank you. So let's take a look at each one of these chemistries one at a time, and specifically the two most popular ones, tris glycine and bis-tris chemistries. Tris glycine utilizes the traditional Laemmli system. It is the most widely used form of separating gels using SDS page. However, it is highly alkaline in its operating pH, as we had mentioned earlier. This is limited by extending running times and gel instability from the hydrolysis of the polyacrylamide to acrylic acid in the alkaline conditions. And although tris glycine is popular, this kind of high pH in its running operation may cause band distortions, a loss of resolution, and artifacts in bands due to protein degradation alterations in run. On the flip side, there is also the bis-tris chemistry, which operates underneath a neutral pH condition. This neutral pH condition minimizes the protein degradation and provides the following advantages over Laemmli systems. It improves the shelf life, which extends the shelf life to 16 months due to improved gel stability. And also, due to the neutral pH, it can create sharper band resolutions and more accurate results. As an example of what this looks like, this particular data set compares on the left-hand side the Invitrogen Bolt Gel, which is a bis-tris chemistry gel, to a traditional tris-glycine gel on the right-hand side. And in it, various different proteins have been loaded, similar proteins for each lane. As you can see from the left-hand side with the bis-tris Bolt Gel, the bands are relatively sharp and clean. On the right-hand side, the tris-glycine gels, the bands are a little bit more separated and different degradation events have occurred. Now, oftentimes the protein degradation that happens with non-neutral pH chemistries are not as dramatic as the example we show here. More often than not, it shows up in diffuse bands or smeared bands. And if you've ever experienced those particular effects using a tris-glycine gel, it could be due to the high pH of the tris-glycine gel. And what happened there is that the protein degradation event occurred in varying degrees. And those varying degrees of degradation had been smeared and separated out as the gel progressed. Now, as far as options beyond chemistry and buffer conditions, there's also a choice between self-casting options and precast gel options. And the materials that are needed for both are different, mainly because of the amount of work that goes into each one. With the self-casting gel option, you'll need not only a casting apparatus, the acrylamide, the TMed APS, stacking and resolving buffers, gel running buffers, as well as a running tank. You also need the time to be able to perform the self-cast itself. The pros, of course, are that you get a fresh gel each time, which is advantageous. However, it is a lot of time and effort. There's casting apparatus failures. Tris-glycine is the predominant main choice in chemistry, and single percentages are typically the only types of gels that you can cast. Inconsistency in the gel cast can also result in resolution inconsistencies. On the flip side, with precast gel options, you simply need the precast gel product, running buffers, and the gel tank. The pros of the precast gel product is that it's more consistent results and sharper bands due to consistent manufacturing practices of the companies that offer them. And the choice of different chemistries also exists, not only in straight percentages, but also in gradient percentages. However, there is a con, which is a higher consumable cost for the researcher. What we'd like to do now is to ask another polling question to the audience as it relates to the type of gels that you typically do. Do you perform self-casting gels or do you perform precast gels? Now, you may be considering that self-casting gels is a typical process that you undergo for protein electrophoresis, or precast gels may be your typical process. But we want to make sure that you understand that there have been improvements made to both self-casting gels and precast gels, and we'll go into each one of them now. Improving upon self-casting gels begins with the primary issues that a user could potentially see when casting their own gels. And the primary issue that most customers see is that the casting apparatus fails, and this is exhibited in either leaking or the breaking of the apparatus itself. The glass plates which are utilized in the systems often chip or crack, which can lead to leaks. The foam inserts, or the manner in which the gel plates are sealed, may deteriorate over time, causing leaks. And this all results in a waste of effort and time exemplified in the repouring of a new gel. Now, our Invitrogen SureCast handcast system, which recently came out this year, exhibits a couple of features that help solve for these problems. Number one, it has a more durable, reusable glass plate. It's thicker and more damage resistant than what current suppliers offer, hitting upon one of the major needs that the customers have when it comes to repouring gels. It's up to 20 times more durable in that respect. Also, it's 100% leak-free due to the wide silicone face-to-face sealing method that we've employed, which provides even pressure seals across all three sides of the plate and increases seal durability over time, leading to less deterioration and therefore fewer leaks. In addition to the apparatus improvements, the SureCast handcast reagents are all stored at room temperature, which can provide additional benefits. And that applies to not only the TMED, APS, and both stacking and resolving buffers, but can also apply to the 40% acrylamide, which is quite unique. Why is this better, you may ask? Well, it begins first with making sure that all the casting reagents are at the same temperature when you begin casting your gels. With all of the reagents at the same room temperature, the temperature effects and polymerization rates are reduced. Having everything at the same temperature means you won't have to spend time bringing all the reagents up to the same temperature. You need to begin casting your gels a lot sooner. Also, with everything at 4 degrees Celsius at room temperature, easier and safer storage is achievable without having to bring everything up to the same room temperature. At this time, we'd like to ask another polling question to the audience. Do you wish you could have loaded more samples into your gels? Yes or no? In addition to self-casting improvements, there have also been improvements to precast gel options. And related to the previous polling questions, one of the primary customer needs when it comes to precast gels is a need to load more samples into their wells. Oftentimes, customers make a choice there between the thickness of the gel itself, either 1.0 millimeter moving to 1.5 millimeter. And this is a need for customers, especially those performing gel electrophoresis on low abundance protein samples, or perhaps antibodies that have a poor or weak affinity and therefore resulting in poor protein signal at the back-end western blot. Poor gel resolution can also be a primary issue with customers, especially those utilizing traditional Laemmli buffer conditions. With the Invitrogen Novex wedge well tris glycine gels, we try to solve for some of those problems. First, namely, we have a proprietary wedge well shaped gel, which allows you to load up to 60 microliters of sample per well. This well, as exhibited by the image on the right, is in a triangular wedge shaped well and available in these particular MIDI gels. In addition, the band resolution and quality has been improved as well to minimize the smiling effects and distortions that you typically see with tris glycine gels. In this data set, we try and explain what exactly it means to have a wedge well when it comes to your protein gel separation results. On the left-hand side is the Novex wedge well tris glycine 10-well gels, along with the various different volumes of sample loaded into each well. On the right-hand side is a typical tris glycine gel from a competing supplier, loaded with the same sample volumes of 20, 30, 40, 50, and 60 microliters. As you can see with the Novex wedge well tris glycine gel, even at 60 microliters, skipping wells in between samples, you do not see spillover in the separation of the gel itself. However, on typical standard well tris glycine gels, you see spillover effects happening in and around the 50 microliter loading volume and the 60 microliter loading volume, thus showing that the Novex tris glycine wedge well gel can load all the way up to 60 microliters in the tail well format without spillover into subsequent lanes. From a resolution perspective, the Novex tris glycine wedge well gel has been shown to have minimized smiling and distortion effects compared to other suppliers' tris glycine gels, as exhibited here in this data set. In addition to providing improvements due to larger load volumes, there's also been improvements that have been made due to band resolutions as a result of gel chemistries, as we had mentioned earlier in the presentation, as well as improvements on gel running times. And the particular product that from our company that we want to be able to exhibit today is the Invitrogen Bolt Bis-Tris gels. Its neutral pH Bis-Tris chemistry preserves the protein integrity with the neutral pH, as we had mentioned, and offers a unique buffer formulation that eliminates the smiles and poor resolution seen on traditional tris glycine gels. In addition, the Bolt Bis-Tris gels also contain the wedge well shaped wells. easily allowing for up to 60 microliters of sample load volume in a 10-well format. But in addition to these two features, the bolt gel can also be run in as quickly as 22 minutes at 200 volts. Here, similarly to the Novex wedge well gel, we've loaded 40, 50, 55, 60, and even up to 70 microliters of sample in a bolt 10-well gel, as compared to competitors' typical standard well gel going up to 40 microliters. And similarly to the wedge well shape, we do not see spillover in the adjacent lanes for the bolt gel. Unlike standard well gels, we do see spillover, thus showing that the bolt gel can contain up to 60 or more microliters of load volume. Here's the same piece of data that we showed earlier, exemplifying the difference between the bis-tris neutral pH gel chemistry versus a traditional tris-glycine gel chemistry. The bolt bis-tris gel chemistry with the neutral pH minimizes protein degradations in run, leading to more sharp and better resolutions in your gel electrophoresis. In this data set, we performed a Western blot using the bolt gel on the top and a competitor's tris-glycine gel, and a typical gel stain on the bottom and a competitor's tris-glycine gel on the bottom as well. And this again exemplifies how a bis-tris neutral pH, along with the in vitrogen manufacturing process, provides a much more consistent and publishable result with minimized smiling distortions in the bands of the gel electrophoresis. Furthermore, improving upon precast gel options, we also have the Envision new page Novex bis-tris protein gel, also including the neutral pH gel chemistry, which preserves protein integrity with the neutral pH, as well as fast, sharp band resolution runs in as little as 30 minutes at 200 volts. Here is a piece of data comparing on the left the new page bis-tris gel with the supplier's tris-glycine gel, again showing that better resolution and better publishable band results can be achieved with the bis-tris neutral pH chemistries. So in summary, for precast options, we presented today the tris-glycine Novex wedge well and tris-glycine options, bolt bis-tris and new page bis-tris options, and for the self-casting gel options, we have the Envision SureCast handcast apparatus, as well as the SureCast handcast reagents. In addition to these particular gel options, we also offer tris acetate options for larger molecular weight separations, tricine options for low molecular weight separations, and various other chemistries such as the native page for typical page electrophoresis. In addition to the improvements on gel electrophoresis gels, there have also been improvements on protein gel electrophoresis tank apparatuses. Primary user issues for standard gel tanks include a back-to-back design, which makes it difficult to load samples easily without turning the tank around, wasted gel running buffers for those who want to run a single gel on their tank apparatuses, difficulties in seeing the gel progression and the ladder progression in run due to the clarity of the plastic utilized, and difficult to judge the buffer fill volumes when the tank is full and at capacity. The Envision Mini Gel Tank makes subtle yet significant improvements to the user experience when it comes to gel apparatus. We have simultaneous visualization of both gels in a streamlined side-by-side tank configuration. We allow for easy sample loading through a forward-facing well configuration. Less running buffer is required, especially when you're running only a single gel. You can load only one chamber at a time if you wish. The white background on the tank allows for easy and simple monitoring of the pre-stained ladders and standards loaded onto the gel. And spillover chambers on the edges allow for consistent and precise buffer fill lines. At this time, we would like to ask an additional polling question to the audience. How fast would you ideally like your gels to run? Under 30 minutes, between 30 and 60 minutes, or over 60 minutes? As a summary of running conditions on the mini gel tank, we like to exhibit a couple of things to note. Both the Bolt and UPage Bistris chemistry gels can run in under 60 minutes, with the Bolt gel running underneath mesh running buffer conditions as low as 20 to 22 minutes, and underneath the MOPS running condition in as low as 35 minutes. The UPage Bistris chemistries can run as low as 30 minutes at 200 volts, utilizing the mesh running buffer, and as low as 42 minutes utilizing the MOPS running buffer. Typical tris glycine gels can run anywhere between 25 to 40 minutes or an hour and a half plus, depending on a denatured or native state running condition. Typical tris acetate gels can run between 50 to 100 minutes, again, depending on the denatured or native state running conditions. As a summary, to choose which gel type is best for you, it's important to understand whether or not you want to run denatured running conditions or native running conditions. In a denatured separation, your first choice is to choose between molecular weight sizes. We had mentioned earlier on that if you're looking at a low molecular weight protein and you want to resolve it among other low molecular weight proteins, a tricine gel would be your best choice. If, however, you're looking at a higher molecular weight protein mix, those above 200 kilodaltons, a tris acetate gel would be the best gel of choice. Those who are looking at proteins in the middle, or the most broad range of molecular weights between 20 and 200 kilodaltons, a typical tris glycine or Bistris gel would be your gel of choice. But between the two, understanding how much sample you want to load onto your gel could make a difference in your ultimate result. And choosing a wedge well shaped gel, either the Novex wedge well gel from Invitrogen or the Bolt wedge well gel, will allow you to load up to 60 microliters of volume. Also, if your gel results result in smearing or smiling effects, choosing a Bistris neutral pH chemistry could minimize those results as well. In a native separation, you will be able to choose between molecular weights, isoelectric points, and protease activity as your predominant choices of protein gels. So the key takeaways today from this session is that the most widely used chemistry is tris glycine because it has no special running buffers. However, it can lead to certain degradations of the proteins in run. That is where a neutral pH system, such as the Bistris chemistries, will allow to minimize protein degradation, improve gel results, and also improve running times. High sample load volumes can also be achieved using traditional tris glycine chemistries such as the Novex wedge well tris glycine gels or Bistris gel chemistries with the Bolt Bistris Plus gels. If you'd like to learn more about protein electrophoresis or downstream Western detection or transfer, we have various technical handbooks at your disposal for both separate, transfer, and detect of the Western workflow. The various URLs are provided here, and they're free for you to be able to download. And that concludes this session today on protein gel electrophoresis improvements. If there are any questions, we'll go ahead and open it up for a Q&A session. Thank you.
Thank you for that informative presentation. Before we get started on the question and answer session, I'd like to remind our audience how to submit questions. You can submit questions by typing them in the Q&A box, which can be found by clicking on the green Q&A button at the lower left of the presentation window. And our first question is, if you see diffuse bands in the stain, is it always due to the gel chemistry?
So the answer to that is no. Although we've shown today during the presentation that gel chemistries can lead to better results. We had shown the difference between the degradations in tris glycine gels versus Bistris gels. Gel chemistry is not the only reason why you would see a diffuse band on a gel stain, for example. Oftentimes, the most common reason is the amount of protein that's actually loaded into the gel itself. Sometimes loading too much protein can lead to smearing or fat bands that will not resolve well in a protein gel. And although oftentimes most researchers and users do not know how much actual protein is in their sample, if they do see a rather diffuse band show up in a gel chemistry that they're used to using and have good separations, typically reducing the amount of protein sample loaded onto the gel can solve for that, especially if you already have a very well-defined signal. This could actually sharpen up your gel results.
There was a difference in running times between MES and MOPS for the Bistris gels. What's the difference there?
So yes, there was a difference there between MES and MOPS, and you saw it in both the bulk gels, the new page gels, and they were not quite significant, but there were at least a few 10 minutes here and there. I believe the bulk gels, you can run the MES running buffer in as low as 22 minutes versus 35 minutes with MOPS. With the new page gels, you can run that gel as low as 30 minutes, and I believe as low as 42 minutes with the MOPS. Typically, this decision between MES and MOPS comes down to the molecular weight of the protein itself. MOPS will slow down that gel run, and by slowing down the gel run, it achieves better separation at the mid to large molecular weight range. MES is much better for smaller molecular weight proteins, and so that's typically the difference in choice when users have to decide between a MES or MOPS running buffer.
Are the wedge well gels all 16 microliter well capacity?
No, they are not. We had shown examples of data today that had the 60 microliter example set at the 10 well capacity. And so the maximum load capacity for 10 well gels are 60 microliters. However, if you are using larger number of wells, such as a 12 well or 15 well mini gel, just from common sense wise, the well size is going to be a lot smaller from the width to width perspective, and so you're going to have a lower maximum loading volume. However, despite the fact that that happens at the 12 to 15 well gel, it's still a larger load volume compared to a standard well gel itself. For example, for the 12 well gel, the maximum loading capacity of a wedge well is 45 microliters. And if you compare that to a standard capacity of about 25 microliters for a 1 millimeter thickness gel, or 37 microliters for a 1.5 millimeter gel, a 45 microliter capacity on a 1 millimeter gel for 12 well gel is still much larger. So even though it's much smaller for larger number of wells, it still is much larger than a standard well gel would be able to provide you.
Why do the Laemmli tris glycine gels have a short shelf life of about 3 months?
The typical tris glycine gel, if you make it yourself, definitely has a short shelf life of about 3 months. There have been various different additives added to commercially made tris glycine gels to allow it to be a lot longer in shelf life, but not as long as a Bistris neutral pH gel, and that's exactly the main reasons why. It's the pH of the chemistry itself. At the basic pH levels, the acrylamide slowly hydrolyzes and forms the acrylic acid over time, which interferes with the proper protein separation as we had seen in the actual gel results. But this also leads to this instability over time allows for a much lower shelf life if you were to make it yourself as a fresh gel, obviously. But additives have been created to be able to extend the shelf life of traditional Laemmli tris glycine gels. The Novex Wedgewell tris glycine gels, for example, have a 12-month shelf life. So not all tris glycine gels have a short shelf life, but more especially the ones that you make on your own.
Okay, we have time for one last question. Questions we did not have time for today will be addressed after the presentation. I'm interested in peptide separation, short lengths of molecular weights of 800 Daltons. What gel is suitable for this?
So as we had mentioned in the presentation, your gel choice can be molecular weight dependent. So for small short lengths of molecular weights such as that, where it's 800 Daltons, you may want to try the tricine gel chemistry, which allows for the separation of the lower molecular weight proteins to be at a larger percentage of the total gel length. So that allows you to separate out the lower molecular weights better, so that you can see sharper resolutions between these low molecular weights. Whereas in a standard broad molecular weight gel, such as a trisglycine gel or bis-tris gel, the low and high end kilodalton or molecular weight proteins will be much more compact in its run and in its resolution. So it's a little bit harder for you to resolve out various different peptides of small molecular weight length. Similarly, with the higher molecular weight proteins, we recommended a tris acetate gel chemistry, because what it will do is it will actually spread out the high molecular weights along a larger percentage of the gel, so you actually are able to resolve better higher molecular weight proteins above 200 kilodaltons. So for smaller short lengths, as the question had asked, the tricine gel is the best. For larger molecular weights, we recommend a tris acetate. And for everybody that's in between, a standard trisglycine or bis-tris gel will do the trick.
I would like to once again thank Jun Ma for his presentation. Do you have any final comments?
You guys coming on to the event today, yeah, we appreciate you guys coming on to the event, and we hope you enjoy the rest of the day's events.
Thank you. I would also like to thank our sponsor, Thermo Fisher Scientific, for making today's educational webcast possible. Today's webcast will be available for on-demand viewing through June 28, 2017. You will receive an email from LabRoots alerting you when this webcast will be available for replay. We invite you to forward that announcement to your colleagues who may have missed today's live event. See you next time. Goodbye.